Hi everyone, welcome to back to our YouTube channel. I'm Desire, and today we've got Sangdon Lee, who has just completed the course Linux Basics. So he'll be giving us a presentation on that. So first of all, as we always require, we want him to show a demonstration on the real robot, and then after that we can get into the details about what he did, how he did his project. So without any further ado, let me hand over the platform to him so he can begin his presentation. Alright, whenever you're ready, Sangdon.
Okay, so I'll have all these things implemented in the terminals interface first because we want to get it ready with the subscribers and the publishers for the different things like the linear, angular, all the information that we need for the robot and the function that we created to avoid obstacles. We do that. Okay, that looks good. And the statistics, print out the. Oh, I guess the copy. Oh, let's see. Okay, there we go. And my. This is a project that I created. So pretty much this is the interface that we use all the informations from this. And then there's the functions where we get and set all the parameters that we get from the robot interface. And finally, the obstacle avoider.bash. So pretty much, I tried to play with the threshold. I didn't change it. I didn't want to be risky, so I used the default threshold that you guys gave me. And since we have to use scan ranges to detect obstacles, I get that from the getters that we set up from the functions that we created before. And then I created my own like thing I want to be specific for the angles for different situations. So this is pretty much, I'll explain that later, but when left or right is blocked, when the front is not blocked, I'll try to command the robot to turn softly. And then when everything is blocked, then I try to say, turn sharp so we have more space. And
Okay.
then it's a 0.5, sleep 2.3 seconds. It'll go for, so this is the duration times the speed. It gives us the radians, but I'm gonna have to change it to degrees. So I pretty much use the calculators, or I Google to see how much degrees it's gonna turn.
All
And
right.
right is negative because if you turn clockwise, it's negative on the circle thing that we learned in high school or, pretty much. So that's why it's negative for right. So it might be confusing for some people.
Yeah.
And
Uh,
yeah,
Clockwise would be negative, so
yeah,
counterclockwise positive. So can we see this running on the robot first, and then we
yeah,
can
sure.
speak about it later?
I guess like it has to wait all the statements a little bit slow, but it's not perfect, but I
Yeah, I
pretty much
think
should.
I think the most important thing is for it to at least to not crash, right? We want it to avoid obstacles. So yeah, it looks like it's doing that well so far.
So do you want me to go back to the explaining the codes, or do you want me
Uh,
to?
let's wait for it to do a couple of more obstacle avoidance maneuvers, and then we can move to that one, yeah,
Yeah,
later.
sure, sounds good. Also, like to, I guess, if you want to be closer to the obstacle, you can decrease the threshold.
Okay. Did you play around with it at some point to reduce it
So I
maybe?
played around with it. Sometimes it just ran into the wall, so I just like, oh yeah, let's try to be safe, even though it might turn multiple times. As long as it doesn't hit the obstacles, it's doing its thing.
Yeah.
So I pretty much like set it back to the default. So I thought there's a reason why you guys set the threshold as 0.3.
Yes.
So I didn't try to, I just like went back to normal threshold.
I saw it just reversed there. What happened? Did you do an implementation of that maneuver? And
Going back.
yes.
So I didn't want to turn like multiple times. So as you can see, it takes a lot of time for you to, turn
Mm-hmm.
to have like, wait for the command. So I just say go back negative 0.1 for 1 seconds and then turn. So we have, it's quicker.
So
We have more space on return.
okay, okay, I see. So are you saying the threshold it exceeds the threshold at some point? Like does it go beyond point 0.3? Does it get too close to the wall in some instances? And or it's just a safety
For my code?
precaution? Yes.
Oh no, no, it's I'll show you. Oh no. Here we go.
All right, all right. Because I want to know like what's the criteria for reversing, right? I thought point 0.3
Oh,
was
I
good enough for
actually
it to rotate. Yeah, you know.
no, it's this case. So when it's the front is blocked,
Yeah.
so instead of turning, I just said I guess it's negative 0.15, negative 0.15, and
Mm.
just back up and just do the turns again. Just only for this case,
Well, okay,
it's
okay,
backing up.
okay. Can you take me through the logic for why only for that case?
Well, it's because we have a lot of elif statements. It's pretty much like handling all the cases when left is not free or right is not free or just one of them is not free or both of them is not free. So based on this, you can see that right is free. So we just turn soft and we have non-free. Then we compare. We compare how much time we have moved. We have to use this distance because we already set up the variables up here for the different ranges like left, and front right,
Mm-hmm.
and right range.
Mm.
And we get the distance to move, and we minus the threshold, so we know how much distance we had before we hit the threshold. And then since we are moving at 0.1,
Mm.
actually you should change that to 0.15 if you want to be specific here. But you saying that we want to move 0.1 meters since that's what we set up as a linear speed, and you divide that to see how many seconds we want to move.
Mm-hmm.
And the seconds we want to move is as long as it's bigger than zero, we know that we have time to move. So we set that up to 0.1
Yes.
and we give its duration, so how long it's gonna move. So it moves its distance, its time, time multiplied speed. So it gives distance. And we wanna stop it
Mm-hmm.
because otherwise it's gonna keep going. And then else is to close. If it's to close, then we just skip the forward motion and we finish the statement right here. And it's a different logic for different cases. For instance, this is when it's not free for the left and if front is free, front right is free, then we just turn right soft because we have more space on the right. It has pretty much similar logics for different cases. It's either turn left soft. So this is pretty similar to each other.
Mm-hmm. So okay, so you're saying that the case that we had where it had to reverse the left was not free, front was
Hmm.
not free, right was the
Hmm.
only free place to go, right?
Hmm.
And if it had left enough distance, so if it had left zero point 0.3 meters in front of it, I
Hmm.
thought it could have rotated nicely, right? But
True.
we noticed that it reversed, so that's what I wanted to understand. What's going on there? Did you think the threshold was not enough for that specific case, and how did you get to that?
Well, so what case are you talking about?
So if you can go back to to the images, so to the cameras that are allowing us to see the robot.
Yeah. There we go. Yeah.
That one, right? So the so if we are, let's use the right frame for reference, right? So we'll always be referring to that. So there was a case when the robot was on the top right, right? So diagonally opposite, so top right, that's when it reversed, wasn't it? So it was facing the wall, it was facing the corner, and it reversed. Then you had to rotate clockwise to go past the solid wall that we have got there. That's the one case I was speaking about.
So when it went backward?
Yes, that place, yes, around almost where your pointer is, yes.
So it's because like the for my cases, as long as it's not close to the threshold, it'll go straight and it'll turn. But
Yeah.
sometimes you have to like the robot could be at different angles, so you can't really have one case to say turn this angle at this point, even though you have that. Based on the angle of the robot current position, it might turn differently, and sometimes it turn twice. And I was just being lazy, so I just didn't want a robot to turn twice. I just wanted
Yeah.
the robot to go back once and then just
Okay.
turn so we have more space in the front.
Okay, so you wanted to like be sure that you are clear of whatever obstacle it
Yeah,
is, right?
definitely. Because
Then,
I didn't want to wait.
uh-huh.
It's a pretty long time, so that's why I did.
What if you had like reduced the time of rotation, right? Did you try that?
Oh, yeah, of course. If we reduce the sleep time, the duration of the turning,
Yes.
then of course. I've tried, but sometimes it turns too much, sometimes it turns too little.
Okay.
Like, so it's really hard to have the angles set up for this like, project because the lay time is was long and I didn't want it to be too short because it might turn too fast. So I just said one simple trick, just go back, we'll have more space and just turn. And that's what I did.
And when it reverses, right? How did you choose the distance that it has to go for? Because I see it almost crashed into the wall, but it stopped, right? Are you also taking in consideration the laser scan data for the back of the robot? Are you considering those for obstacle avoidance as well to make sure that when it reverses, it doesn't hit an obstacle? Or you?
True. So I should have thought about that. I should have added the back ranges. So when I have that logic, when it's like less, the way you apply the same formula for distance to move, time to move, just make sure it stops when it reaches that point. I should have added that. But I based off the distance I chose was, when it goes front or when I tested, it doesn't really like exceed a lot. But I guess what you're saying is when it's at like the middle right here, when it's I don't even know what that is, like a stone thing, it might crash into them.
Yes, it
So
might crash into it when it reverses. Yes, that's
yeah,
why I'm asking.
so I should definitely add that logic for the back range. I should have I don't know why I thought of that, but yeah, I should add the distance to move logic so you make sure it's safe when it backs off.
Yeah, yeah. Well, it will make your program a little bit more complex, right? But after you have
True.
implemented the reverse maneuver, I think it is important to take note of that as well, right? Because you will have cases where it reverses into an obstacle if you don't do a handling of that, right? So
True.
yeah, but
Oh, I think does it have the back back range? Oh, they don't have that. Hmm. Oh, right here. So we just get that gas can back rate range. We'll probably add it here where we get it, and then we pretty much do the same thing. We declare the variables. We want to echo it, and then like this. We set up the back free range just to make sure that back range is bigger than the threshold, and it actually help us a lot. And we can pretty much use a similar logic that we use here, just to give the robots to see how much free distance that we has before it is cl too close to threshold.
Yeah, it would be exactly the same, just flipped around, right? But
Yeah.
so yeah, completely. All right, so I think for the obstacle avoidance, we've done some justice to that. So, can you take us through your robot statistics script and give some detail on that?
So it's like it's pretty much just calling the variables from the function. So every time it goes or shifts or moves, it gives like the position of the robots for X, Y, Z.
Yeah.
And and it also has the orientation as well and the velocity. It
Mm-hmm.
has acceleration, everything. So it's pretty much having the statistics of the robots during its movement.
Okay, and calling the like functions that are responsible for
Yeah,
giving you
pretty
those
much.
values.
Yeah,
Uh-huh.
I had an error here because I'm not really familiar with the Linux. I thought it was okay if I'm calling the variable, I can just use the curly brackets, but apparently you have to use the this parentheses. So I don't know why I had an error. So I looked up and you're supposed to use parentheses when you
Mm-hmm.
call it.
Yeah, that it's part of the journey, right? It's part of we
Yeah,
having to learn
And
the
I
the
was used
you.
to Python, yeah, you know.
Yeah, exactly. But it's a good thing you did get to discover some of these nuances about
Hmm.
the scripting language itself. So yeah. All right. So I think that's some justice done to your project. Do you have any other implementations that you wanna give a highlight on specifically?
Um, Highlight. So I think it's important is when you like set or get the the parameters from the interface,
Mm-hmm.
it's because when they print off, they might say like the speed is this, and based on these parameters they have, I'm getting the first one. So you should be careful. You should print out this first and see where the parameter you want is located to
Mm.
make sure that you want that.
Yeah,
Put it
very
like a
good.
yeah. So you should be careful because I made sure like I printed it and see it. I'm not sure like what they said in the print statement, but it was located in the fourth one, so that's why I mean you guys have print $4 for everything, but I wanted to make sure that it's same case for settings and everything.
Yeah. I think it's a very good thing that you did that because you need to know where your parameter is, right? So part of
yeah.
knowing where it is actually printing it out and then knowing how you're gonna write that function and extract that specific one. Because
Hmm.
if you just do it randomly, you might not have it in the location that you expect it to be. So yeah, very
Hmm.
good on that one. Yes.
And then just play with the functions. You can create different turns. I guess you can create like a different speed functions as well.
Mm-hmm.
So for this case, you don't really need to do with the speed. You just have to deal with the turns. And I think should be careful how much sleep. All this matters. Like
Mm-hmm. How did you get to the 2.3 value? Did you have to test? Um,
yeah. So uh, I pretty much what I did was like I told you, I did a calculation of turning this to degrees.
okay.
So I calculate the degrees. I believe this is like it's not that it should be below 60 degrees
Okay.
and this should be over 60 degrees.
Uh-huh.
And I just based on the position of the robot, let's say if it's gonna be a little bit slanted when it's left is not free.
Mm-hmm.
So I just said we want to go like 45 to 60 degrees range before it turns too much. That's
Right.
why I chose. And then when we are too close, the wall, we want to turn way more. So I did to the 60 to 70 degrees. So that's why I chose the 60 degrees range for the turn right sharp.
Uh-huh. Okay. All right. All right. Very, very well done. Very well done on that. Okay. Thank you so much, Sangdon, for your presentation. So,
Yep.
I think we hang around and we finish our
Okay.
conversation. All right, everyone. This was Sangdon Lee's presentation, and would like to thank him for coming and giving us this details about what he has done and how he did it, and also the logic behind it, because we think that is very important. So I'd like to encourage all those of you who would want to try all the courses we give certification on to do so, and then you can come and showcase your work. So until next time, keep pushing your